Okay. So today we're going to talk about factorial analysis of variance. This is, I keep saying this, the most important lecture so far. This is the most important lecture so far. This will take us more than one class. We'll have to finish this up almost certainly on Thursday. Right. So why isn't this connected? Oh, now it is. Okay, good. So I made up some data. Don't worry about it. Okay, but I've got some data here that I made up. These are percent correct, which we would, of course, normally transform, right? Like we talked about last week. And what I've done here is I made up an experiment where we've got a memory test, and we're giving people a list of words, and they're going to recall them either 5 minutes after studying the list, 1 hour after studying, or 24 hours after studying. Okay, and you'd probably get something like that. Those numbers probably wouldn't be that far off. Percent correct. Okay. So that's the, don't worry, this should not be anybody, don't look at that and go, ooh, Dave gave me a thesis idea. We know that memory decays. That would not be an exciting idea, just letting you know. So, okay, this is interesting, but what about we did another memory experiment? And in our second memory experiment, we're going to study levels of processing. Levels of processing can go from shallow to medium to deep, which sounds as, what's the word I'm looking for? Inexact as it is, but shallow level of processing is me giving you a list of words and saying count the number of ascending and descending letters. So like a D is an ascender, a P is a descender. All you're doing is looking at the word. Medium level would be count how many vowels there are. Even better, how many syllables there are. Yeah, let's do that. How many syllables? And the final one is rate the word on its pleasantness on a scale of 1 to 7. Okay? And this was discovered, this effect, the levels of processing effect, was found by Gus Craig and Bob Lockhart in 1972. It's literally the most cited paper in all of cognitive psychology. It has, I think, 18,000 citations. It's kind of ridiculous. And I know those guys, which is kind of cool because they were profs of mine at U of T. I can tell you that it will, again, don't try this, it will work, for your thesis, it will work. It's a great idea, but it was tried before any of your parents were born. So, not a big deal, let's not do that. But the question, let's say, fine, we do this, we find we get an effect. And it would work. It always works. Okay. Oh, remember how we beat the Americans in hockey? Remember that? That was great. Wasn't it, though? Wasn't it awesome? Even if you didn't like hockey, right? You watched it anyway. In 1972, we beat the Russians. And then we beat the Russians again. They're kind of like Russian. Anyway, what level of retention interval should you have done the level of processing experiment at? 5 minutes, 1 hour, 24 hours? For that matter, what level of processing should you have used for the retention level experiment? So should you have used medium or shallow or deep? Now I know you know where I'm going with this. I don't expect you all to gasp when I say you could do them both at once. Ooh! No, of course not. But if you look at this experiment, what we've set up here is we've got low, medium, and high levels of processing, 5 minute, 1 hour, and 24 hour retention intervals. And then we've got, and these are, the G just means group. I've got 9 groups. So each G is a bunch of subjects. So like, I wonder if I put, I've only given this lecture 31 times. No, I don't think I have anything there. Okay, so let's say there's 5 people in each. So group 1 has subjects 1 to 5. Group 2 will have subjects 6 to 10. Group 3 will have subjects 11 to 15, etc. And I'm using subject here rather than participant. It's my old stats prof, I've told you that many times, he said, you know, we should, instead of saying participants, you want to be neutral, let's call them experimental units. Let's go with that. That's not pejorative at all. We're just calling them like they're things. subjects. I gotta stop ranting and raving about something that happened 25 years ago. Anyway, you see how this would work? So we got two variables. We've got one independent variable, which is retention interval. The other independent variable is going to be level of processing, and then we have 9 groups. This is what's called a 3x3 factorial analysis variance design. Or a 3x3 factorial design, anyway. Right? We all know that one. Questions so far? Okay. So now we're going to obviously have to model this. We need a structural model so we can figure out how to analyze something like this. So like that, transition there. So the model is x equals mu plus alpha plus beta plus alpha beta plus epsilon. No, that alpha and that beta are not the same as type 1 and type 2 error. There are only so many letters in the Greek alphabet. So they're used in more than one place. But I'm not saying it's not confusing. Okay, so believe me. There's only so many letters in the Greek alphabet, so we're going to use those. So what this is saying is that any score, I don't know why I did that with the things today. I just losing the will to live. Grand mean plus an A effect. There's two variables, A and B. So in our case here, maybe that's retention interval, or maybe it's level of processing, whatever. Because the second one, B, that's the B effect. That's going to be the second independent variable on its own. Oh, that's new, the A-B interaction. That's how A and B work together. So A and B work together. That one wasn't as interesting, an error. Just like that, it was kind of fast, like that. And of course the leftover stuff, error. Okay, so x equals mu plus alpha plus beta plus epsilon. And, which is just grand mean plus A effect plus B effect plus interaction plus error. This is really not any different than the last model, we're just throwing more terms in. We still have mu, we still have main effect, we just have two of them now. We have two effects, not just one. We have two we call main effects. We still have an error, and we have some, this is the new thing, is the interaction. Now you've all taken 21, 27, so you've all run into what interactions are, but don't worry, I'm going to force it into your brain soon. That'd be so much easier if I could just sort of hold you there and force things in through your ear holes or something. Well, that got a little weird, sorry. I told you I'm on 1 hour of sleep, so things may get a little weird. It's not really an excuse for talking about assaulting you through your ears. That's a little weird, but oh, things taken out of context. Whenever things like that come out of my mouth, I always hope that the university president isn't walking down the hall. All right, more explanation of this. So we can look at A and B, how they act on their own. So we can look at retention interval, and we can look at levels of processing, and how they act on their own. We can also look how they interact, how they act together. What is interaction? It's kind of like the whole is more than the sum of its parts. In fact, it literally is that. So it's saying that the variance in scores is due not only to the effects of the variables by themselves, but also to the variables working together over and above them by themselves. Okay. So this is that the effect of one variable changes depending upon the level of some second variable. That's what what's called a two-way interaction is. The effect of one variable changes depending upon the level of some second variable. And sometimes it's hard to get that into your head, like what does that mean? Sometimes an example helps. Okay. There is an effect of, depressing as it is, there is an effect of your gender on how much money you make. It's not right, it's ridiculous, it's getting better, but it's still true. There's still a difference in earnings between men and women. Right? This is not the time to come at me with, boy, well, actually, no, it isn't. You're wrong if you think that's not true, okay? I've got lots of data to back up what I just said. Also, I've got a whole bunch of women in this room that probably tell me that their lived experience is exactly that. Okay, that's fine. It's also a little harder being a visible minority than being part of the majority. True? And in fact, visible minorities make a little less money than the majority. That sucks. It's wrong. But to deny it would be stupid. So you don't deny it, you put things out in the open, you talk about it. But you know what's really hard, probably? Being a woman of color is probably harder than just being a woman or just being a person of color. In fact, yes, that's the extra bit, that's the interaction. And I picked those examples just, and I realize it's a depressing one, I think it hits home, and I think we all know these things. I could have used something positive, but I don't know. Again, I'm operating on 1 hour of sleep. So it's the effect of one variable changes depending upon the level of some second variable. There's something over and above being a woman and over above being a person of color. Right. Okay? Let's graph. Let's show this on a graph. This might be a little easier. Okay. So here is B. Whoa, please. Okay. Don't. It's showing okay here. Okay. There's B1, and this is, this is B1, and this is B2. Hard to see the different colors, at least for me. And then we have A1 and A2. And if you look at this, the average of between B2 and B1 at A2 is up here, and then between B2 and B1 is down here at A1. So A2 is bigger than A1. There is an effect of A. You can also look and show that and see that B2 is always above B1. There is an effect of B. But the effect of B is bigger at A2 than it is at A1. Do you see that? Right? The lines are further apart. That's what I'm saying. The lines are further apart. There is an effect. The effect of B is bigger at A2 than it is at A1. And A1 is level 1 of variable A. So let's say we're doing our level of processing and our retention experiment just with 2 levels. So this would be A1 is low levels of processing and A2 is high. And B2 is a shorter retention interval than B1. Yes. Something like that. So again, the difference between B1 and B2 is smaller at A1 than it is at A2. I should have moved that out of the way. It was supposed to move the graph out of the way and make it smaller, all kind of cool looking. Didn't. I guess I worked too much on making flames make a model here. The effect of B changes depending upon the level of A. So they're both true. So if the effect of B changes depending upon the level of A, that also means the effect of A changes depending upon the level of B. Okay? You're saying the same thing, just switching it, right? Okay, I'm going to stop now and ask you if you have any questions. And don't feel that any questions are stupid, please. Like, seriously, I mean, it's important stuff and I want you to understand it. So if you have a question, ask it. Because I can see some of you have looks on your faces that are like, let me take a picture of your face right now, show everybody. They all look like that. Like, I was just standing here so I could see you. But looking out, there's a few other looks. Yeah. So seriously, questions. Or questions as we go along, we can always do that, but you have questions. So far, is this sensible? Okay, again, the effect of A changes upon the level of B. It's bigger. So look at this one here. It's easier to see probably the effect of B being bigger at A2 than it is at A1. The lines are further apart. The lines are further apart. That's all that means. Okay? Okay? Questions? Are you good so far? I think you're good. I think you're not sure you're good, but I think you're good. Because you all passed 2127, you can't be in this room. So, okay. But don't feel bad about asking anything. There are no dumb, well, that's not say. You know, whenever anybody says there's no stupid questions, that's a lie. It's a tactic to get you to ask questions, because they're stupid questions. Like, Dave, how long have you been a monkey? Well, that's a stupid question. Why do you have a third leg growing out of your head? That's a stupid question. Why is the sky purple? That's a stupid question. I'd answer them all, though. Okay, so we're good? Okay. So, back at the model, x equals mu plus alpha plus beta plus epsilon. So, let's look at some assumptions. So, the model has assumptions. And the first assumption is that the sum of all the effects, all the alpha i's and beta j's, sum to 0. That just means all the treatment effects sum to 0. So if you're in group 1, like A1, maybe your score goes up by 2. That means all the people's scores in group 2 go down by 2. They must. You will see as we go along that there's no other way that can work. It's just a property of the universe. Okay? Because of the way this model is going. So the same thing happens at the beta j's. The I and the j are just like 1, 2, 3, whatever group it is. Okay. And we're going to do some examples a little later, and you'll see where this, I think you'll see how this follows. The sum of the alpha I beta j's equals 0. That's the interaction effects. That means if you're at A1, B1, your score goes up by 1. But if you're at, let me just show you here. So what these assumptions mean, let's do the first one. Sum of the alphas equals 0. So that means everybody in, we're going to do this. What, that should be a 2, you dummy. B1, B2. Okay. By the way, people listening on the internet there, I was calling myself a dummy, not one of the students. They're all incredibly brilliant. Well, let's say nice things. I like you guys. You guys are pretty cool. It's going to be fun. 2606 class, I got problems with some of those guys. But that's a whole different thing. A whole different thing. Right, so we got, this is a 2x2, very simple design. Right, simplest possible factorial design. So if everybody with all the a's must sum to 0, so let's just say that all the a1s get +1. That means all the a2s get -1. Okay. Same with the b's. Well, let's make them all go up by 3. Or down by 3 in B2. And then the interaction has to sum to 0. This is where it gets kind of complicated. +1, -1, -1, +1, because they have to sum to 0 both horizontally and vertically. Okay? And now we can actually look and figure out what these numbers are. 1 and 1 is 2 and 3 is 5. -1, -1, 2, that's going to be 1. Let's see what we have here. +1, -1, -3, and -3. Is that right? Yeah. Assuming I did that properly. So you see those are they all sum to 0. They all sum to 0. I mean, and the meth that I smoked before class. I shouldn't have said that. I said the quiet part out loud. I will never. There's certain drugs. I have a very libertarian attitude about drugs. You can do whatever you want. There's certain drugs I don't think I should take, and one of them are pretty much generally stimulants. I'm kind of edgy anyway. I think me on cocaine or meth would be a really bad scene. So, I just don't. No. You want to do that? Go nuts. Just don't do it when you come to my class. Do it for all Paul's classes. I just don't care. Okay? Have fun. It's not. Oh, some of the errors. The error is normally distributed independent. That's just notation. It's normal and independent. with a mean of 0 and a variance of sigma squared. All that means is this assumption is also an irregular analysis of variance. It just means that error is randomly and normally distributed. It means if I know Victoria's score, I don't know Andy's score. But if I took all your scores and looked at how you deviated from the means, it would be a nice normal curve, and it really weirdly would be. The world is, statistics is kind of cool sometimes. The central limit theorem is awesome. So that actually comes out of the model. This is basically telling us that, well, telling us the restrictions on the possible values of alpha and beta. Okay. Questions so far? More questions or lack thereof? Okay, like I said, when I work through some more examples, you'll see in a second. I think you'll see that how this works. Okay, then the F test has assumptions. Because of course we're going to do this with F. We need homogeneity of variance. Once you know that, just all the variances are equal. They're never always equal, but as long as one isn't roughly 4 times bigger than the other one. Random samples. Yeah, sure they are. We can violate the crap out of random sampling. And we always do. When people give their, I hope you all go to the honors thesis presentations on March, what is it, 29th, I think? That's what it is. It's the last Friday in March. You should go because you get an idea of the kind of work that you're all capable of doing, and that you'll see your student, like your classmates, your student colleagues, basically. You see the kind of work they're doing and have done. I won't be there. I'll be in Albuquerque at a conference. Usually that happens. Paul does an impression of me in introducing my students. So, which I kind of like. Like he plays it up like he does the blind thing and everything, which I find hilarious. But everybody else gets really uncomfortable. So it's. He did a talk once when Paul first came to work here. About maybe it came in 2007. About 2009, he gave a talk to the faculty. We used to give talks locally. So Paul, I introduced Paul because I was running the colloquium series. So I introduced Paul, and then I sit down, and then Paul comes up to me, and he said, "Thanks, Dave. You see me? I'm right here." And everybody was so, we planned this in advance. Everybody was so taken aback and feeling uncomfortable. Paul and I was laughing at everybody. It's good. The one upside, like when you're disabled, you can make fun of yourself, and it makes people uncomfortable, and it's almost more fun than. Oh, yeah. It's great, right? Yes, you know.
Oh, yeah.
Yeah, you know.
Oh, yeah.
And you can make people really uncomfortable, which is kind of fun. Like, I can tell you, by the way, that's why you have kids, is to make them feel embarrassed. You know that too, right? Yes. Kindred spirits here. So, yeah, and then it's
Or
one of
they
the fun.
embarrass you.
Oh, well, yeah, there's that. But you just got a stupid kid, who cares? But yeah, it's kind of, it can be fun.
30 and still embarrass my mom pretty frequently, so.
Excellent. Excellent. Yeah, I remember walking with my daughter down, like in the station mall. She's about 10 years old, and I just started singing. Dad, stop it! I said, well, it's not going to affect me, and it's actually making you feel very uncomfortable. I'm enjoying this, so I'm going to keep doing it. You shouldn't react. To this day, she's 31 years old. She still reacts to things. My wife says, "Don't feed him. Just stop it." We can violate random samples. We know this actually. You can run simulations and find out that you can violate the random sampling assumption of it for F. Like you can violate the crap out of it, and it still works. So you have to worry. That's another one. That's an assumption we make that doesn't matter. Like it is an assumption of the test, but it doesn't matter. You can literally have binary populations, zeros and ones, and it works just fine. Okay? Because what happens, central limit theorem, you still get nice samples, still have nice normal distributions, so you're okay. But technically, you're supposed to have a normal population. It doesn't matter. The variance one matters. We can't violate that really too badly. We violate the hell out of the next two all the time. All the time. Like when I did my PhD work with chickadees, black-cap chickadees, they were just the first ones I caught. I didn't randomly sample chickadees throughout the world. They were the first, 10 that I was able to get into a trap at in the woods. It's like, but the work, because what we do in psychology are fundamental processes, right? We do a lot of times. And I was doing a fundamental thing about cognition. So, you all should work that way, please.
So you collected the chickadees from forest?
Yeah.
And what did you do after when the study was done?
We let them go.
Oh, okay, perfect.
Yeah. Yeah, we let them go if they were in good shape. If they were in good shape. If they were clearly not in good enough shape that they would, because when you take a wild animal and you put it in a cage, they don't always love that. And it takes them some, well, they like it pretty quickly though when they find out they get fed every day and it doesn't go down to -20 at night. So they get fed, they get water, it's great. But some of them don't react very well to it. Some of them will lose feathers, and if they lost, let's say, their tail feathers, they can't really fly properly anymore, so we wouldn't let them back and go out because they just become a snack for some other animal. Every year when we would go trapping, we would get birds and we would know they were our old birds because we put leg bands on them with their ID, and you pull them out and go, no, you don't get to stay at the Hotel Spadina this year. you got to stay last year. And you put them back out in the wild. And some of them we killed. And, look at their brains and things like that. Yeah. But yeah, we were releasing them, most of them were released back into the wild. They're wild animals. You can't, we had a capture and kill permit, but they really Fish and Wildlife want you to be nice, so we release them. Nice thing is chickadees aren't really an endangered species. Like for example, house cats kill over 20 million chickadees a year just in Canada. House cats are murderers. No, I'm not kidding. I don't let your cat outside.
Invasive species.
Yeah, they are an invasive species. They don't belong. We can violate these too. Just don't violate home chickadee ferrets. And let your chickadees go. Okay, I'm going to give you some numerical examples to show you how this kind of breaks down. What I'm going to do when I do these examples is I'm ignoring individual subjects. So I'm giving you, these are group needs, 9 and 7, 3 and 1. They are not, these may be made up of like 10 people in each group. I'm not going that far. I could, but we'd be here all day. And this is really to show you how this works. So we know the model is x equals mu plus alpha plus beta plus epsilon, plus alpha beta plus epsilon, right? So what we're going to do is we're going to remove the different components, different sources of variation from this, and we're going to go from the term that is the most general to the ones that are the most specific. So let's start with the grand mean. The grand mean applies to all cells. Okay. So the grand mean here is 9 and 7 and 3 and 1, which is 20 divided by 4. There's 1, 2, 3, 4 is 5. The mean of those 4 numbers is 5. That's all that means. Right? 9 and 7, 16, and 3, 19, 1, 20. Divided by 4, you get 5. That's all it is. And now what we're going to do is we're going to remove that grand mean. We're going to just take 5 out of each cell. Okay, we'll take 5 out of each cell. Questions so far? Okay, let's do that then. We take 5 out of each cell and we get this. 4, 2, negative 2, negative 4. Now, if we take the grand mean out, and remember all those other effects should sum to 0, right? So remember, some of the alphas, some of the betas, some of the alpha betas must all sum to 0. So that means that what we have left should sum to 0 already. Let's see. 4 and 2 is 6. Oh, it sums to 0. And that's not because I cooked up this example. I cooked up the example to make it all whole numbers, that we don't have to deal with fractions. Because, amazingly, some of you people, I don't think you guys, but I have met people at your level of schooling who can't deal with fractions, which is great. So I just thought I'd do it with whole numbers. But that's the only way this is cooked. You do this with other numbers, you'll get quarters and halves and stuff, but it will work. It'll always sum to 0. Okay. So do you see what I did? I just took 5 out of each of those cells. And now what I'm going to do, we're going to look for the effects of A and B, and we're going to start by looking at the effect of B. So we're going to sum across, or you'll hear me sometimes say collapse across A. 4 and 2 is 6. Minus 2 minus 4 is negative 6. And there are 2 observations for each of those, right? So on average, B increases your score by 3, and B1 does, and B2 decreases your score by 3. Hey, look, it's sum to 0 again. And again, you can figure it was because I cooked this, but I cooked these numbers just so there are no fractions. Oh, yeah, please.
Sorry.
Yeah, no, please, sorry.
So, why do we divide by 2? Is it because we have 2 numbers?
Yes, exactly. Perfect. I love when people ask a question and answer it themselves. I don't have to say a thing, except this part where I say how good it was and waste much time. No, you got it perfectly. And again, if you're not sure, you think, is that what happened? Just ask. This is literally my job. Don't you used to hate when you guys ever have your teachers say things? I'm not just doing this for the good of my health. Did you ever hear that one from like your grade 2 teacher? I was a smart ass kid, as you probably guessed. I had my hand up once and my teacher said that. I said, but don't you buy things with the money they pay you? Isn't that good for your health? I must have been a lot of fun to teach. Constantly sitting there being like 8 years old going, I'm smarter than you, bitch. Which I clearly, probably was, but I didn't know as much stuff. Also, I didn't call women bitch. Like, that's not something I did. Especially when I was 8. I was really into following rules. I was really good at that. My brother, no. It was always the same. My brother would get into class and he was in class. Oh, are you David Broadbeck's son? Yeah. Brother? Yeah, I am. Dan's like, but I'm not Dave, okay? I can play guitar. See, whereas in high school it was different. We were a lot more trouble. You know, the librarian who hated us. My sister's 9 years younger than me. Years later comes. This librarian's telling my sister to be quiet in the library in grade 9, and she says, what's your name? My sister says, Stephanie Broadbeck. Are you related to Danny and David Broadbeck? They're my older brothers. He just walked away. Oh my God, there's more of them! Smart ass kids, I hate them. I was a pretty good person, pretty good kid. I was a bad kid, but I was a good person. So what happens, we're going to take 3 out of all the B1s, and we're going to take negative 3 all out of the B2s. Now, what does that mean? That means that we're going to subtract negative 3. So what we're actually going to do is add 3 to all these, right? You don't use subtract a negative, it's a positive, right? I see a lot of nods going, oh yeah, grade 4. Okay, so yeah, you remember you all learned all this stuff? This is when I'm never going to use this. You are right now. So your teacher was right, you're all wrong. So let's take 3 out of all these. We should get what? 1, negative 1, negative 1, 1, shouldn't we? Oh, look, that's what we got. Now, what happens here, it's negative, it says negative 2 and positive 2 divided by 1, but 2, I'm sorry, is going to be positive 1 and negative 1. Yes? I just summed across or collapsed across A. And again, you can check that you did this right because we've taken out the B effect and look, it sums to 0. So every time you do one of these things, you can always check, did I do this properly? They should all sum to 0, they do. And across B, because we've taken them out, they should sum to 0 and they do. Across A, we haven't taken them out yet, they shouldn't necessarily sum to 0 and they don't. We're doing it properly. So now we're just going to do the same thing as before, but it's to the A's, not to the B's. And what we end up with, oh look, there's nothing left. Well, the only thing that could be left is interaction. Remember I said we're not dealing with individual differences in my examples here, because I could, but it would take, the example would be a whole other 20 minutes to do this, and it's not really instructive. So, nothing's left, so there's no interaction. Because the only thing that's left is interaction. And if there's nothing left, there's no interaction. There's just what are called main effects of A and B. There's just main effects of A and B. Okay, questions? Oh, yes, please.
So I have a question on the previous slide.
Yeah, let's go back. No problem, let's go back.
So
Yes, okay, is that it?
one more.
No, one more. What am I just, oh, yeah, no, you're right. I just did that. Okay, here we go.
Okay. So B1.
Yeah,
So B do the 4 minus 3, right?
yeah,
And then 2 minus 3, right?
yeah.
So B2, I just don't get it.
Okay, so B2, let's go back. No problem. And, okay. 4 and 2, 6, -2, -4, -6. Take away 3, take away -3. If you subtract -3 from -4, you get -1. -4, no, minus -3
Two negatives makes it
makes it positive. -4 minus -3 equals -1.
Okay, there's your.
Yeah, because the negative and negative, right? You're taking it out.
Thank
I
you.
just saw a light bulb go off over your head.
happened to me 5 minutes ago.
Oh, no, believe me, when you haven't dealt with subtracting negatives for a long time, like literally since about grade 5, grade 4, like, this feels weird.
Thinking in my brain, it was like -4, like -4, -3.
Yeah, exactly.
So it's like -7.
No, exactly. And the problem with that is that's what you have to think. -4, we're taking away. And that's what you have to think, oh, okay, so we're actually adding. Yeah, it is weird to think of. And again, remember learning this in school? This is a number line. 0, 1, 2, -1, -2, and you're sitting like, why are we learning this garbage for right now? That's why you were learning this. Or if you go into other things that are much more math heavy, you would have dealt with it earlier, but there's a reason you learned all this stuff. And there's a reason that it isn't like a negative. Again, you're subtraction. What's the opposite of subtraction? It's addition. But yeah, I remember learning all about number lines thinking, why am I learning this crap? This is ridiculous. I was good at it, so it's fine, but it's still ridiculous. Okay, so let's go back. So you good? You good? Yes? I saw the light bulb. We're good? Other questions? Okay, so this is where we ended up, and we ended up with nothing, so there's no interaction. One of the things you could do, and I saved this because I didn't want to, give you a spoiler, but you can graph it at first. What you should do, in fact, if I was doing one of these, first thing I'd do is graph it. I'd start by graphing. So I just put those cell means into the, actually I literally just threw them into a spreadsheet and said, make a graph, please. Like, that's why the scale's funny. I don't care, right? This is for illustrative purposes only. It's not something in the paper or anything, it doesn't matter. But you can see that the difference here is the same size. There's no interaction. The lines are parallel. There's no interaction. Parallel lines need no interaction. Okay? Let's do another one. I've completely given up at this point on telling you what the variables are, because I'm not a very creative person, and I can't think of any examples. We got dependent variable, and then we got A and B, and they're independent variables. Make up your own experiment, okay? Whatever you think it is. But here we got a big gap here. You should be able to just look at this right away and say there's an interaction here. Look, we go from 20 to 0. Whereas here we go from -10 to 2. That's a difference of 12. That's a difference of 20. There is an interaction. There must be. Just by looking at that, you can see. Or this way, 0 to 2 and 20 to -10. Difference of 2, difference of 30. There is an interaction in these data. Right? Okay, so we start with the grand mean. Go from the most general to the most specific, so the grand mean applies to everything. 20 plus 0 minus 10 plus 2 divided by 4, that's 12, which equals, divided by 3, divided by 4 equals 3. So we just remove the grand mean from all of these. Let's start, though, by showing ourselves that right now this does not sum to 0. 20 minus 10 is 10, and then that doesn't sum to 0 at all. Right, so we haven't done anything yet. Once we take 3 out from all the cells, I bet it sums to 0. Because the only thing left are things that should sum to 0. And, oh, lo and behold, that sums to 0. Right? 17 minus 3 is 14, minus 13 is 1, minus 1 is 0. Oh, yeah, it sums to 0. I did it properly. Or, coincidentally, it worked, which is pretty unlikely. So the A effect is plus 2 for A1 and minus 2 for A2, right? Because it's 2 observations, plus 4 divided by 2, minus 4 divided by 2. Okay, good. Again, sums to 0. And the effects sum to 0. And the only reason that they are whole numbers is because I cooked the numbers, but you could put any 4 numbers like that and it will work and it will sum to 0. It will always work. I think if you take a look at this and see what we're doing, you'll kind of look at that and go, I see why too. It must work that way. Okay. Did everybody get that? So is we okay? Because I can go back to the slide. You want to go back?
Yes.
Please.
I want to know again, why is it 2?
Because 17 minus 13 is 4 divided by 2 observations. We're taking an average.
Okay.
That's all it is.
Okay.
Yep, good question. Thank you for asking. So they sum to 0. So we're going to take 2 out of all the A1s. I'm going to take negative 2 of all of the A2s. Okay. So let's do that. We end up with 15 minus 1 minus 15 plus 1. Oh, things are starting to happen now. Notice how, again, all the cells sum to 0. We're still doing it properly. The grand mean's gone. And so the columns. So we actually we've taken out A, right? Look, 0, 0, because we've taken those out. We have not taken out the B effect, which is going to be plus 7 and minus 7. Right, because it's plus 14 and minus 14, 2 observations. So for B, we have an effect of plus 7 at B1 and minus 7 at B2. Again, they will always sum to 0. This is a property of these of the way the world works. This has nothing to do with anything other than that. Like, it's not that I made it work like this because the numbers are okay. And you can prove it yourself. Just put 4 random numbers into a 2x2 table and start breaking them down, which is a good way to practice, by the way. Might want to make sure that you're not getting a lot of fractions, but even with fractions you can do it. Use a calculator if you're not comfortable with fractions. Okay, so we're going to take 7 out of all the B2s, or sorry, the B1s. We're going to take negative 7 out of all the B2s. Oh, look. Hey, we have an interaction because we have stuff left over. Plus 8, minus 8, minus 8, plus 8. So the effects do sum to 0 still, look. And interaction effects have to sum to 0 across and up and down. And they do. And all together. And they do. They don't have to sum to 0 diagonally. It's not like Hollywood squares or something. Yes, refer to the game shows that were on. Your parents were over. If it was all zeros, we have no interaction, which was what we had last time, right? Yeah, we had no interaction in the last example. Here we have one. Well, prove it to ourselves by graphing it. As I said, I didn't start with a graph, but I would, if I was doing this, I would start with a graph. Makes it easier. Oh yeah, there's interaction. it's hard to tell where the main effect is here, to me, just by eyeballing it. Let's see, that's halfway between, that's a small one. I can't quite tell if there's a main effect there. I can tell it that there's an interaction. The lines cross. That's the opposite of parallel. They cross. So. Okay. So I hope those two numerical examples helped a little bit understanding the logic of how the model works. By the way, if you wanted to, like, oh, here's our, what's the example I have up on the board here. I could actually get the sum of squares from this. So let's see, it was, I did what? Plus 3 for B1 and minus 3 for B2, right? So we got plus 3 squared plus 3 squared plus 3 squared plus 3 squared, 9, 18, 36. The sum mean square is 36. Or sorry, sum of squares is 36. Those are squared deviations. I just took the deviations and squared it. That's magic. 3 squared twice minus 3 squared twice. So while, like I said, it's sort of theoretical what I'm doing here, it actually does apply to how the math ends up working. All right. Now, the thing about interactions is you have to interpret them. Like any data, you can do the math and make a graph, but can you tell me what that means? And interpreting interactions is not always easy. Especially when you interpret main effects in the presence of interactions. So this is not so bad with what's called an ordinal interaction. And I don't know that, well, let's do that. So it's harder with a disordinal interaction. Now here's what I'm talking about. An ordinal interaction is one where you have an interaction, but the lines do not cross. So if we had this, there's A1, there's A2, and there's B1, and there's B2. Okay? So this example here, you can see that the effect of B is bigger at A2 than it is at A1. But I think, at least I, feel comfortable saying that there's a main effect of B. I am very comfortable saying B2 is bigger than B1. I don't have to talk about A at all. And I am also comfortable saying that A2 is bigger than A1. I can just talk about that. I can say that. There's an interaction there, because at A2, the effect's bigger. The effect of B2. So this is what's called an ordinal interaction. Okay, that's an ordinal interaction. Whoops. Need to do that. Let's go back. It's just sitting in the pocket of my hoodie and I touched it and started to. Make sense? You good?
Oh yeah, I just can see it. That's
Okay.
what- just
Oh, is that? Oh, yeah. Okay, good.
Yeah.
I'm
I just was
remember
making sure I
doing
had-
that. I'm doing that. Lots. My friend Diane sat beside me in personality, and I think she drew all the graphs and all my notes.
Oh yeah.
Scott, thanks. It's kind of cool. We're still friends. It's kind of neat. All these years later. So maybe you guys will be friends like all these years later. That's what's going to happen. That's what happens. When you help somebody with when you help someone with a graph, you become friends. That's how it works. So that's an ordinal interaction. Now let's just change this up. This. Okay. So I can still see there's an effect there. I think we can all see that. Look. A2 is bigger than A1. By the way, if you're listening to this on the podcast version, there'll be a picture on the blog post because I'm about to take it right there. not hard, Dave. Just take a damn picture, okay? Okay. There is a main effect of A here. A2 is bigger than A1. Sure. There's a main effect of B, because it looks like B1's higher up than B2. Do you feel comfortable talking about the effect of B without mentioning the effect of A? Well, without mentioning the level of A? No, right, you can't. Like, I can say, yeah, B1's bigger than B2, well, at A2. Well, overall it is 2, sure, on average B1's higher up than B2, but weirdly at A1 it switches over completely. I can't talk about them without mentioning the other variable. So with a disordinal interaction, I can't talk about the main effects without mentioning the other variables. If I can't do that, I probably won't even interpret the main effects. A more conservative approach, and the book mentions this, that you can interpret main effects here, but some people say not to. So a more conservative approach is don't ever interpret main effects in the presence of interactions. I think that's horseshit. I don't think that's the way you should do things. I think if you've got something and you can talk about it, do it. But if you legit can't, and you can't here, I can't talk about B without mentioning A with the one on the left. I just can't. Statistically, there's an effect, of course. But I can't talk about it without talking about the interaction. Now, you might say, hell, what are we doing then? We find interactions, are they bad? Oftentimes, you know, we deal with a complicated bunch of data. We deal with how living things think. And we can't watch thinking. We have to look at the products of thinking. Psychology's hard. Right? Those who want the thoughts diets. Oh, shut up. No, it's hard, because it's harder. Watch this. Want to see you do some physics? 9.8 meters per second squared. Happens every goddamn time. Every single time. Now do that with something in psychology, some basic thing. Everybody scores a little bit different. Even though we all show decline in our memory, some people's memories are better than others. What we do is hard. Interpreting is hard. So some people will tell you do not talk about interactions in the present. Not talk about main effects in the presence of interactions. I'm not quite that conservative about data, and I usually am pretty conservative about data. But what I would say here is, I would say, look, I would not talk about the main effects here. At least I would interpret them. I'd mention them in the results section. You can't not. But I wouldn't talk about them in the discussion. I would be talking about this. And like I said, our science is hard because it's almost always about interactions. Very rarely are we doing things that are only about one variable. Now, some of us deal with very fundamental processes, stuff I do, right? Stuff Lane does. So, you know, really sort of basic memory and cognition and neural basis, those things. That's pretty basic, and that should be the same in everybody. But a lot of times you're dealing with very complicated variables that are kind of fuzzy. Personality and social variables are incredibly fuzzy. Makes it hard. So as much as I make fun of Paul, because he's basically a sociologist, not a scientist, these are jokes, guys. I don't think that at all. The kind of work that he does is hard. It's hard because it's fuzzy. Stuff I do is actually quite a bit easy in a lot of respects, because it says, how many words do you recall? Oh good, write that down. That's easy. He does some of that, but also there's, you know, that social stuff really fuzzy. So a lot of times we get interactions because we want interaction. We don't care about main effects. A friend of mine in grad school, all he cared about was interactions, pure interactions. Just crossed lines, no main effects. That's always what he wanted. So a lot of our theories deal with interactions. You might think, well, why would we ever do this? Why would we design such complicated experiments? In psychology, biology, in the life sciences, we deal with hard things that often have interactions. It's hard to isolate some of the effects that we're interested in with living things. All right. Do you have any questions today? We're stopping early today because there's a lot, and I always stop early. There's a reason for it. That was a lot I just threw you. But it also gives us like 15 minutes if you have answer. I will be posting also a video about how to do a Factorial ANOVA in SPSS. It's probably exactly as you expect. The thing is, it's no longer is it the ANOVA command. It's going to be under what's called general linear model. Okay. There's a reason I keep talking about all these models, because sometimes you actually have to type the model in. Okay. But you'll see, I'll post a video on the LMS, probably on my website as well. So, see how to play with this stuff. Assignment 3 has also been posted. I saw that you got assignment 2 in. I was wondering, I woke up going, why do I have 35 emails? Oh, what's happening? It's one of those reply all things at work, isn't it? Because that happens, man.
So much.
Yeah, you know what I do now when I get the reply all thing comes across to me? I just type in unsubscribe. It doesn't do anything, but I think people get the idea that I don't like reply all thing. I got a professor from computer science actually emailed me to apologize for doing reply all. It's like, oh my God, I'm actually affecting people who I don't even work with. This is great. So, any questions on the stuff today? Like I said, we're going to stop here, and it's planned to stop here with 15 minutes left. It even says that in my teaching dossier when I applied for promotion. It literally does. Must have dropped that and you get it?
Yeah.
Okay. What the hell's going on? They're passing notes? Are we in grade 4?
I know, but I
Right,
can't.
you guys good?
I can't.
Okay, go home. I'll hang out here a bit in case you have questions. Okay. So if you're listening to this on the audio and the podcast version, this is the second part of this. If you're watching YouTube video, this happened. This just happened right here. We were talking about interpreting interactions and how interpreting interactions in the presence of main effects, interpreting main effects in the presence of interactions can be problematic. And we talked about ordinal and disordinal interactions. So if you have an ordinal interaction where the order of the main effects is preserved, whoops, that's not really even an interaction. Let's just make that a little bit there. So something like this, you can refer back to, if you're just listening online, you can listen, you can take a look at the post and see the same drawings. B1 here, B2 here. So the one on the right, assuming, I don't know what it is on the post, but the one on the board here is the one on the right is a disordinal interaction. You can see how there probably is main effect of both A and B, but interpreting it would be very difficult. Talking about that main effect in the presence of that interaction is very hard. You can't say A is bigger than B because you have to say sometimes. You don't have to say that here. Here you can say A is bigger than B, or sorry, A1 is bigger than A2. You just say that, and it's true. Here, you can't. A2 probably is actually bigger than A1 in this graph. But we can't say that because it's true at B1, but at B2, in fact, A1 is bigger than A2. Right? So a disordinal interaction, this guy here, is much more difficult to interpret when you, as far as main effects go. And I would go so far as to say don't interpret main effects in the presence of interaction if you have a disordinal interaction. That's the more sort of liberal stance, the more conservative stance. Scientifically, this has nothing to do with politics. By the way, there's an election today, vote. Democracy is under threat. Vote, please. When you look at this, you can see that interpreting these main effects, the presence of interaction, is going to be difficult. Like I said, this is a more liberal approach. Is the one I take, sort of conservative. I think more liberal approach. But probably the only time I take a liberal approach with data. I'm quite conservative with data. But a lot of people say never going to interpret that main effect because there's an interaction, and that's a totally reasonable thing to say. People say it, and it's fine. I think it's a little bit. I like to look at it as a case-by-case basis. Again, I'm a little more liberal with this. So when I say a case-by-case basis, does it fit all the previous research that there are two main effects in interaction? If everybody else finds that, can I not talk about it? But if no one else talks about that when they interpret their data, I probably shouldn't either. So I would do it on a case-by-case basis. Does it fit with my theoretical framework? Stuff I thought about in advance, not stuff I went, oh, I wonder why that happened. Let me see if I can post hoc explain that. No, stuff you thought would happen. Okay? All right. Questions on interpreting interactions a bit here? So you see what I'm saying is that it's difficult, or it could be difficult with disordered interaction. Okay. So let's partition the degrees of freedom into sums of squares here. So remember the model, again, is x equals mu plus alpha plus beta plus epsilon. So this, it should be the case that sum of squares total equals sum of squares A plus sum of squares B plus sum of squares AB plus sum of squares error. I'm just turning all this into sums of squares. And you're wondering, where's the sum of squares for main effect? Or sorry, the grand mean. That doesn't make any sense, because everybody has the same score for grand mean. It would be 0. Okay. Okay. Yeah. All right. So, yeah, sum of squares A is the square deviations of rows and columns. Okay, so if we're thinking of A, think of a very simple 2x2 design. A1, A2, A1, A2. So, and then we would have different groups here, group 1, 2, 3, 4. And this group 1, let's make this a whole example. So we could say that group 1 is subjects 1, 2, 4. Group 2 is subjects 5 through 8, ... Group 3 equals subjects 13 to 16. Okay, so we have 16 people in this experiment. We have 4 in each group. Okay, so 16 people in each experiment, 4 in each group. So the sum of squares for A is going to be the column means. That's the means for each column, because I've set up A's at top and then B's at the side. That's why. So standard deviation of column means from the grand mean. Okay. Sum of squares B is standard deviation, square deviations, of row means from the grand mean. Okay. So rows go across, columns go down. You can't remember why that is? Columns hold up buildings. They go up straight and up and down. And I literally still think of it that way. So don't feel bad if you go, which one's column again? It's like how I remember how inequality signs work. The alligator's mouth goes towards the biggest piece of food. I mean, I still remember that from like grade 3 when the teacher taught us that. Or grade 2. Miss Byers, that bitch. Oh, sorry. Did I say that out loud? She took my hockey cards. Oh, yeah. But she taught me about inequalities, and I still remember it. So maybe she got her job. Yeah, well. Still, she took my hockey cards. I was 7 years old. Anyway.
Did she return it?
Oh, yeah. After my father said he was going to call the police because she stole my hockey cards at the parent-teacher meeting, that was fun. There's nothing better than watching your dad own a teacher when you're 7. Do we have to get the police involved? Or are you going to give my son back his property? It's the best thing. I miss my dad all the time. My dad died almost 20 years ago. I miss him so much, but I really miss things like that. One time there was a couple kids bullying my brother and I when we were camping. And my dad just, out of nowhere, steps like out of these woods and goes, "Anybody here want their head cut off?" Kids ran away. My dad was a really nice guy, by the way. This makes him sound like he's horrible, but he was also a little intense. I come by this honestly. Take everything about me, except the amount of education, multiply it times 10, that's my father. Everything behaviorally or about my personality, yeah. So you can see he must have been a real peach to live with. Anyway, questions on this? This makes sense, right? They're just deviations of the means for A and B from the grand mean. The weird one, the new thing here, is sum of squares for AB. That's going to be our interaction sum of squares. That's different. We haven't had that before. This is squared deviations of cell means. These are the means for group A1B1, A2B1, A1B2, and A2B2, which is the world's lamest droid. Thank you. Nothing? Okay. Let me group R2D2. I've now explained the joke, and it still isn't funny, which is tremendous. So it's these means from what we would expect given the row and column means. So if we've got a column mean of, I don't know, 8, I just made up a number, and the row mean is 12, but our score in here is 10, that's exactly what we would expect, right? Because 8 and 12, the average of 8 and 12 is 10. So we'd actually expect that. So we'd actually get 0 there. But what if the number in there isn't 10? What if it's 26? There's something else going on there. It should be 10, because if it's 12 and 8, the average of 12 and 8 is 10. Right? If the average here, if the average of the row is 12, the average of the column is 8, and there's an equal number of subjects, the average of those two numbers is 10. Right? You don't get that? The average of 12 and 8 is 10. 12 and 8 is 20. 20 divided by 2 is 10. Get it now? I'll show you my work. Okay, so, but we don't get 10. What if we get 26? Well, something else is going on, the interaction. That's what the interaction is. It's the extra stuff that we still haven't explained. And sum of squares error, remember I said there are different subjects in each of these groups. Those are the means of each individual minus the cell mean. So, I don't know, it's group 2, right? So subject 5 was in group 2. Remember group 2 had a mean of, when I said 26, right? Let's say subject 5 gets 23. So that's the mean of just between 23 minus 26. We're working this out. Squared, so that's going to be 3, 9. So it's 9. And we do the next person. That's what sum of squares error is. That's the square deviations of individual scores from cell means. So the cell mean is the score for each group. The grand mean is the score for the whole, for everybody. And then we have column means and row means. So if you're calculating these things by hand, it's time to stop doing these things by hand. They're going to start getting mathematically no fun. You'll start making mechanical errors you can't find, and I can't find. Right, Carter? Carter and I were looking at his the other day. I was like, I know there's a mistake here. We were both looking like, there's a mistake here, but I don't know what it is. But I know there must be one because the numbers are wrong, and that happens, right? This is why you start using a computer, because you will make mechanical errors just because there's a lot of stupid calculations. They're easy calculations, but it's easy. But if there's 20 of them, I make a mistake. But if you do it by hand, you won't need all these row means, column means, cell means, and all that stuff. All right. So more precisely, okay, look, you're never going to do this by hand. Don't. Please don't do it by hand. No, seriously, don't. But let's look at it. It's hard to see, sorry. Right? Ironic. Thank you. Irony. X minus, that's the grand mean squared. This, okay, row mean, column mean. So this is going to be the sum of squares for A, this is sum of squares for B. There's the sum of squares for the interaction. And that's, look at that, 3 summation signs. That's the sum of squares error. I'm not even going to go through what these mean, because all this is saying all that stuff I said before in words. It's all putting it into mathematical notation. That's all that is. This is just saying sum of squares total equals sum of squares A plus sum of squares B plus sum of squares interaction plus sum of squares error. Okay? And you can start getting, you get really bogged down in looking at equations eventually. And I don't want us to do that. I don't think it's useful. this level, I just don't think it's a good idea. So let's not worry about the equations so much. But realize they're all squared deviations from the cramp. Look at that. It's all minus g, x bar sub g, x bar sub g, x bar sub g, x bar sub g. They're all deviations from the grand mill. Dude. Pretty neat, eh? Pretty cool. All right, so let's work this out. The degrees of freedom. We have n minus 1. All designs have big N minus 1 degrees of freedom. We have a minus 1. So if we have two levels of A, in our experiment here that we've set up, we have two levels of A. So we have 1 degree of freedom for A. We have two levels of B. So we have 1 degree of freedom, I'm sorry, for B. The interaction has A minus 1 times B minus 1 degrees of freedom. So in our case, it's going to be 1. Let's show you how that works. Let's make a bit bigger of a design over here because it makes it a little more instructive. Okay, so if we had, well, let's just make a simple one. We'll make it A2. That's A1, A2, B1, B2, B3. We're going to make this a 2 by 3, that's called. So what are some possible, and just, I want you to yell out, no, yell at them, please. There's no reason to yell. Only I may yell. So just give me a number. We're going to come up with possible values for how much the interaction raises or lowers scores. Now remember, interaction, those scores have to sum to 0, right? Okay. So how much, let's say this is +1. Give me another number. Which that one?
Plus 2.
+2, where do you want to put it?
B3.
B3, A1?
Yeah.
+2. Oh, wait a sec. We have to put something here. So we've lost 1 degree of freedom. Oh, wait. I don't know that we have any more degrees of freedom. Because that's now fixed, and that's fixed, and that's fixed. This must be, actually, -3, right? Which means that's +3, which means that's -1, which means that's -2. They have to be. They must sum to 0. We have 2 degrees of freedom. Okay. So it's A minus 1 times B minus 1 degrees of freedom. So if we had a 3 by 3, we now have 4 degrees of freedom. If we have a 8 by 8, we have 49 degrees of freedom. Okay? Questions? Does this make sense? So it's just A minus 1 times B minus 1 degrees of freedom. Finally, the error has A times B times N minus 1 degrees of freedom. So we have 2, in our case here with our example, we have 2 levels of A, 2 levels of B. That's 2 times 2, and then we have 4 subjects per group. So we have 3. So 2 times 2 is 4 times 3 is 12. We would then have 12 degrees of freedom for error with this design here. Okay? All right. How about now? Questions now. This is good. You guys are awesome. That projector, however, is not. Come on back. Come on back. There you go. Okay. Now, remember the simple ANOVA. In simple ANOVA, that's the one way. We call that simple analysis of variance. The expected value of mean squared treatment was epsilon plus tau. Yes, I know it's n times sigma squared sub epsilon. I'm just going to call it epsilon sub tau. Okay. And we would divide that by mean squared error, because the expected value of mean squared error is epsilon, and we get to determine how much treatment effect we have. And that's how analysis of variance works. So we have to do the same thing here for a factorial design. So we have to find out the expected values for mean squared A, mean squared B, mean squared AB, and of course mean squared error. I'm not going to derive them for you because I don't think it would help anybody. And I don't know that I can still do that, so I'm not going to do that. What I'm going to do is tell you what they are. So, okay, the expected value of mean squared A, this is exactly what you would expect. Alpha plus epsilon. By the way, the notes might be wrong. So the downloaded ones, this has been updated and corrected. So I don't know if I've updated and corrected the notes. You'll see in a second. The expected value for mean squared B is beta plus epsilon. That's the effective B plus error. The expected value for mean squared AB is alpha beta plus epsilon. It's so nice. And now some of you just realized that alpha beta is where we get the name for the alphabet. That's where that word comes from. The first two letters of the Greek alphabet are alpha and beta. That's why we call it an alphabet. Oh, I just saw that one go off over your head. Yes? Did you get it? Yes? So, does this make sense so far? Like that, those are the expected values, and we have the expected value for error. And to isolate these effects, all we're going to do is divide mean squared A by mean squared error, mean squared B by mean squared error, mean squared AB by mean squared error. Because that isolates, because think about this. I bring markers and I can't find them. Okay. If we had, let's see, that alpha plus epsilon over epsilon, right? The epsilons cancel, and we are just left with the effect of A. We're always dividing one mean squared by another. So alpha plus epsilon divided by epsilon. The epsilons cancel. We're left with alpha. Alpha beta plus epsilon divided by epsilon. The epsilons cancel. Yay! Okay, it's going to get a lot more complicated. I'm sorry. Blame the universe. This is not my fault. This is not my fault. But we're going to, so far, we're just going to divide by mean squared error and everybody's going to be happy. For our F tests. So there's going to be actually 3 F tests, right? There's going to be an F for A, an F for B, and an F for AB. That's fine. Yay, everybody's happy. Uh-oh. Yeah, there's a however. There's always a however, isn't there? These expected values only work if you're interested only in those values of AB. So in other words, if you're only interested in, we had retention intervals as our example, 5 minutes, 1 hour, and 24 hours, and you're not interested in making any other inferences, so what happens at 18 hours? I don't know. Just because you can draw a graph and connect dots doesn't mean that you can say anything what happens between the dots. We all do that, but you shouldn't really do that. So these expected values only work if those are the only values you're interested in. Which is weird, but I'll explain why in a second. But so far, we're okay.
I have a question.
Well, we're not okay. So far, we're screwed. Go ahead.
I'm sorry.
No, don't be sorry. I'm just messing around. Please, don't be sorry.
I'm still stuck there.
Stuck over here, okay.
Yes. How does the alpha plus epsilon by epsilon, like we cut the epsilon because it is applicable for both alpha and epsilon.
So,
For example.
so here what we're trying to do is we're trying to isolate the effect of A, okay, which is denoted by alpha, right?
But when we do numbers,
Yeah.
okay,
Yeah.
do numbers.
Yeah, okay.
So, for example,
Yes.
we're doing 2 plus 4 divided by 4.
Yeah.
We can only do it, like we cannot cut 4 and 4.
No. This is, I'm thinking about this conceptually, don't worry about it. What we're trying to do is get it so we can isolate it, but yeah, the F test in fact takes into account. But if you had, this really is 2 fractions. This is alpha over epsilon plus epsilon over epsilon, isn't it?
Yeah.
Well, that's just, let's cancel and become 1. Okay.
Yes, but
Yeah.
still it is alpha divided by epsilon. Okay.
Yeah, so they cancel sort of, what this does, with this quantity, it's actually sigma squared sub alpha divided by n times sigma squared sub epsilon. And what that quantity does is that isolates at least the effect itself divided by the effect of individual differences without only the, but it removes the effect of, but it takes out, yes. But it takes out this part here and just adds it on as one, so it allows us to sort of standardize it. That's what's going on. So think about it sort of conceptually, don't worry about it as actual fractions.
Okay.
Yeah. Yeah. What you're doing is it's allowing you to sort of isolate alpha divided by epsilon. Is basically what's happening here. Okay. This is called a fixed effects model when we're only interested in those levels of the independent variable. But that's not really hardly ever what we do. Like, that's not, we aren't only interested in those, are we? What if we randomly chose the levels? So instead of 5 minutes, 1 hour, and 24 hours for retention intervals, we put all possible retention intervals into a hat and we chose 3. What kind of weird experimental design is that? It's a weird experimental design called the random effects model. That's what it is. And it's something we hardly ever do. You might ask why I'm telling you about this. You'll see in a moment. So in a random effects model, here are the expected values of mean squares. They're different. So mean squared A is alpha plus alpha beta plus epsilon. And B is beta plus alpha beta plus epsilon. And error, that's good. This is the same. And there's error. So now it's different. So if we've randomly chosen our levels, which we never do, but if we did, our F tests are different now. Yep. So now if mean squared A and B are divided by mean squared for the interaction becomes what's called the error term for A and B. It's the same thing here. Yeah, it's just allowing us to sort of isolate alpha and beta and not worry about alpha, beta plus epsilon. So it's on its own. Okay? So it's what it's getting at is the extra variance accounted for simply by that. Or this. Now for the interaction, we actually divide it by the errors. Weird. But look, that's because of the expected values. Yeah. You might be saying, Dave, but do I have to work out expected values of mean squares every time? No, you don't. SPSS will do it for you. You just got to make sure you tell it if it's a random effect or a fixed effect. If you don't tell it it's a random effect, it assumes it's a fixed effect. That's the default. Okay. Okay. Now, what about we did this? It's called a mixed model, where A is fixed and B is random. Yeah, I think you might have sigmas instead of epsilons in the notes, is that right? Or did I fix it? Apparently I fixed it because no one's nodding. Okay, or you're not paying any attention at all, which is a real mistake in here. I can actually tell you're all paying attention anyway. Mean squared A is that. Now this is A is fixed. No, that's not a typo. I know it's not intuitively pleasing at all. It's also the right answer. Okay, so, and unfortunately this is something, unless you are incredibly mathematically inclined and you want to look at a proof, you're just going to have to memorize this. Sometimes the world works like that. But the nice thing is, as I said, if you're using SPSS or any stats package, that's a fixed factor. They go, oh, I got it. And there's other ones too. I don't know if PSPP does that. So what PSPP does is it just assumes everything's a fixed factor. And if you've got a random effect in there, what you have to do is by hand calculate, just take the mean squared for one and divide by the proper mean squared. Which is doable. Like I said, it's not a typo. This is the way it is. I'm not going to explain why it's too much trouble. And I don't know that it would help anybody. The explanation is you're all Catholic and I'm Pope Dave the First. I'm infallible. God told me this. God, I hope I didn't offend anybody. Okay, you good? Now, so we're assuming with a random effects model that we've actually randomly chosen. The reason that we get these differences is we can actually, we can model the randomness, right? The whole thing's based on randomness. Think about central limit theorem is all about randomness. Like this is, because of the extra randomness in there, that's why it changes the expected values of the mean squares. So we're assuming the random effects model at the levels of the random factor are randomly selected. Literally randomly selected. And independent of each other. And how often does that happen? It doesn't. Right? And that's just not a thing. Move my mouse pointer, there we go. So really what are we usually using? A kind of sort of mixed up nodal random effects kind of fixed. We just assume we use fixed. Because unless you randomly chose your levels, those expected values are just wrong. Like they're not just like, they're wrong. The closest thing is a fixed effects model. When would we actually use a random effects model? Well, there are times when we might have a random variable, like a random independent variable. What if we were testing tire wear of, like it's a Canadian Tire Company, maybe the Canadian Tire Company, and they're testing tire wear for some winter tires. Thing is, winter tires wear differently here than they do in Victoria, BC, where people don't put winter tires in their car because there's no snow. But even in southern Ontario, people put winter tires in their car, and they don't have as much snow as we do. Right? And then there's places like in Newfoundland, you put studded tires in your car. Because you guys have no idea what snow is. You don't know. You think that's a lot of snow? So you put your studded tires, so they wear differently. So are we going to use every possible city in Canada for this experiment? No, we're going to randomly choose 4 or 5. Oh, that's an independent variable, and we randomly select it. That's the case. So usually we're doing like a lot of times field experiments, things like that. You might be randomly selecting locations. But you're almost always not. So just assume it's a fixed effects model. And I'm telling you about this, and you're thinking, well, you just said we never do this. And you gave me a bizarre example about tires. My thesis is not going to be on tires. There's a reason I'm telling you about this. It all comes together at some point. This is going to allow you to do all kinds of other cool things when you know about randomness, random effects. So the question you have to ask yourself is, did you actually randomly select your levels if you didn't just use a fixed effects model? I have seen someone use random effects pretty rarely. It's becoming something people talk more about, though. The idea of fixed and random effects is becoming something that's trendy. People are starting to think, oh, maybe this is a random effect. Maybe it's not a fixed effect. So people are starting to talk about those things. And I found that out reading some papers, and I thought, oh, that's interesting. People started to talk about this, and then I got an email from a buddy of mine. He says, my friend Rob in Emory, University in Atlanta, and he's like, my grad student said this is fixed, talk about fixed and random effects, and do you remember this, Dave Mann? Because he calls me Dave Mann. And I said, yes, I remember it. We were taught it in graduate school. I was your TA. Do you not remember anything I taught you? I was also in the lab with you for 4 years. And you would always come to me with your statistics. And I'd say, we'll do it like this. And it turns out, in fact, he just, didn't learn anything. But anyway, hi, Rob. We're very good friends. All my friends live in different places. It's no good. Why can't they all just move here and not have jobs here? Because they wouldn't, I'd love it. Rob could move up here and bring his whole rhesus monkey lab up here. That'd be awesome, but I don't think so. Did you randomly select the levels? No, you didn't. So use a fixed effects model. And then here's what our ANOVA summary table would look like. Right? So the ANOVA summary table for simple analysis variance only has, treatment or an error or between groups, within groups, whatever. Here we just go A, B, and error. This is just summarizing the last 8 slides. But you're seeing, oh, Dave, you're saying to divide by mean squared error all the time. Yeah, this is only true for fixed effects, right? So it doesn't work for random effects. You have to remember those things for random effects. Or for mixed models. Okay? Like I said, though, the nice thing is modern software, they didn't used to do this, by the way, you have to always do it by hand. Modern software now just allows you to pick a box. It says something's a fixed or random effect. So you end up with something like that. So knowing these things, knowing where these entries go, this is a great way I can test you on all kinds of things with one question. Just leaving a bunch of these blank and having you fill them in. And Vera's looking at me like, oh, I'm going to be doing that. My eyes are bad and I can still see how big the smile is in your face. What I'm saying is there's going to be another one of those fill in the blank summary tables on the next test. Okay? I'm just telling you this, right? It's going to happen. It's going to happen. And you'll smoke it because you see all this. And you have all your notes during the test. This is right here. By the way, on a test or a quiz, unless I tell you it is fixed, that I've randomly selected something, they're fixed effects. Because that's how the world works. Though, as I said, people are getting a little bit more sophisticated with their analyses. All right. Questions? All right. So, these designs can get bigger than this, because we can have a third variable. Hey, look, I threw in C. Okay, I know. So now you have 8 groups. We got, this is a 2 by 2 by 2. Right? A 2 by 2 by 2 completely between subjects. Factorial design is what you would call this. Or just, yeah, 2 by 2 by 2 factorial. Or a 3-way design, sometimes you hear it called that. It's just bigger. Notice that every time we add a variable, we double the size of the experiment, though. We literally double it. Just if we have 2 variables, if we have 2 levels. What if we have 3 levels? We triple the size of the experiment. So we suddenly now, instead of having to get, what is this? I said 16 people. Now we need 32 people. And it starts to get a little bit more unwieldy when these things get big. So let's talk about how we're going to look at these. I'm not going to break down one of these for you, but I'll show you that what we have now is we have 3 main effects, A, B, and C. We have 3 two-way interactions, A, B, A, C, and B, C. And we have a 3-way interaction, A, B, C. Wow, okay. Fine. Wait, what? There's 4 interactions? How? What? I can't. I quit. I'm going to change my major to English. Because I speak English already. I'm going to take English. What am I going to go to England? Nothing? This isn't that bad. What's a 3-way interaction? It's that the 2-way interactions change depending upon the level of some third variable. What's a 27-way interaction? The 26-way interactions change depending upon the level of some 27th variable. There aren't 27-way designs, so don't worry about it. I'm saying that technically that would be right. So a 3-way interaction just says that the 2-way interactions, the ones you're used to already, change depending upon the level of some third variable. And I'll show you a picture, I think, or I'll draw you a picture, one or the other. Well, first I'll show you what the model is. Here's the model. It is now x equals mu plus alpha plus beta plus gamma plus alpha beta plus alpha gamma plus alpha beta gamma plus beta gamma. I forgot that one, plus epsilon. ABC. Just ABC. Oh, that's a gamma. That's a Greek letter gamma. The sort of Y-looking thing. It's a gamma. We use Greek letters. It's a mathematical thing. When you run the Greek letters, you use Hebrew script. It's really weird. There was one guy from Israel when I was in grad school. He's like, "Oh, great, we can find." He said, "Yeah, you got to run out of Greek letters first, though." So he's like, I was like, "Oh, well, now you don't have to teach me the Hebrew alphabet." So x equals mu plus alpha plus beta plus alpha beta plus gamma plus alpha beta plus alpha gamma plus beta gamma plus alpha beta gamma plus epsilon. Look at how big this is now. Look at how many F tests we have now. 1, 2, 3, 4, 5, 6. We're going to have 7 F tests in this one analysis. It might look like that. Hey, a 3-way interaction. That's what that is. This is it. Just look at the panel on the left. Ignore the one on the right. That's an interaction. Right? Lines aren't parallel. And look at the one on the right. C2. Ooh, this is an ordinal interaction. This is a disordinal interaction, but the interactions are different depending upon the level of a third variable. Right? The third variable here is C. You could graph this differently. You could graph it A by C, and this would be B1 and this by B2, and you'd still see the same. And sometimes it's hard when they're to think about these things in abstraction, but if you put these things into, try to make up an example, you think about, what are two variables that interact? I don't know. Oh, memory test type, there's different kinds of memory tests, and retention interval, we could stick with that. And then, I don't know, two groups. What are two possible groups? People who, I don't know, let's say that this group studied for 10 hours and this group studied for 10 minutes. Now you can see, oh, I can see how that could happen. The interaction effect would change depending upon how people study. Oh, that's a two-way interact. Okay. Should I actually look at the computer probably, or the projector? Where should I pray? Where should I direct my prayer? I beseech you, oh projector. I've never used the word beseech. I don't even know how you'd spell that. B-E-S-E-A-C-H, spell it? So let me look that up while I keep talking. That's gotta be right? Or is that even a word? Am I screwing that up completely? It's beseech, right? That's a word? That's one of those.
S-E-E.
It's S-E.
It's two E's.
It's two E's. I just assumed it was E-A. Okay, I've learned something today. Cool. Okay. So, okay, I want to ask any questions on this stuff before we go to the advantages and disadvantages. Okay. We can study interactions. That's the biggest advantage. And frankly, there are entire fields that depend on interactions. I'm a comparative psychologist. I study different animal species memory. Oh, memory, and that memory can be affected. Oh, what about if they're remembering two different things, like they're remembering for spatial information and color? And then there's two different species. Oh, look, I just described my PhD thesis. I mean, the whole thing was about three-way interactions, right? Like, a lot of our theories are about, I said this the other day, psychology, biology as well, our life sciences are complicated. We don't deal with simple things. They're complicated systems, and because of that, we have interactions all the time. And once you've done this a few times, it's relatively simple to interpret. It's relatively simple. Okay, what's the bad side? Are they fixed or random or mixed? And that's, like I said, people are starting to pay more attention to this now, but it's still a question you should ask yourself. Usually just say it's fixed. These things can get very big very fast. Okay, these designs can get very big very fast. So let's just see how big. So put a 4-factor design in, A, B, C. Now we're going to do D. Now here's the model. X equals mu plus alpha plus beta plus gamma plus delta plus alpha gamma, beta gamma, alpha delta, beta delta, delta gamma, alpha delta gamma, beta delta gamma, alpha beta gamma. It sounds like that bunch of bad fraternities. Alpha beta gamma delta plus epsilon. Yeah. Look at how many F tests there are. I think it's 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, sorry, 16. No, 15. It's 15. I got it right. Holy jump. Now, I can't think in 4 dimensions. I can interpret graphs in 3 dimensions. That's easy. Because I live in a world that has length, width, and height. It makes complete sense to me. Yes, I know it's 4-dimensional because of time. I'm moving through time. We can time travel. We just only go forward. We're all time traveling right now at exactly the same speed. I can't imagine graphs that move with time. It doesn't work like, my brain doesn't work like that. I can Chloe's just not, no, I'm not, yours doesn't either. Yeah, exactly. Anybody else, like, if anybody can do that, way to go. My old stats prof Ian used to say, it's pretty easy, Broadback. All you have to do is imagine the graph kind of moving throughout time, and the way it moves, that's the fourth variable. And I said, well, you can do that. I said, can you do more? Oh, I did you color, so you do fifth, and like a colder color means it's lower. Hotter color means it changes color and it moves in time. I said, you think that's an effective way to present data, Ian? Because no one else does. You're insane. That's that, 15 FNS. Right? So this might get a little difficult. Right? So you have all those mean squares. That's stupidly huge. Like, you can't. I have one time in my life seen a four-way interaction, like in a paper, seen a four-way interaction that I understood. It was I think it was handedness, left and right, sex, male, female, and two other variables I can't even remember, and it was something to do with spatial processing. It was something I read, like, and I'm not kidding you not, like 35 years ago, so it was in grad school, or undergrad actually. Was that undergrad 35 years ago? No, I was not. It might have been 40 years ago. I was only 19, 40 years ago. I wasn't reading papers when I was 19. 37 years ago. Now that we've nailed that down, that's very important. When I was in third year, I was in a class like this. Okay. Questions on this stuff? Because I'll show you some SPSS stuff in a second. We'll stop the recording because that's not going to be interesting for anybody. Well, it might be interesting, but to hell with it. Came off wrong, sorry. I'm a little bitter. I shouldn't have said that. Questions on this stuff? Now remember there's a quiz on Tuesday about this stuff. All right, so let's stop.